So in my last class I was discussing the problems based on torque, parallax theorem and perpendicular theorem and movement of inertia, and a few more problems are there, and after that we can go to that is the angular momentum and the conservation of angular momentum. Now we discuss one or two problems more on this torque and the parallax theorem. Now here we are taking that is a problem, a cylinder of a mass m and radius r is resting on a horizontal platform which is parallel to the xy plane. So that's why this is the xy plane is taken, x is here and again the y. So xy plane, and a cylinder of a mass m and radius r is resting on a horizontal platform which is parallel to the xy plane with its axis. With its axis the platform is given a motion. So that's why here the cylinder is along that y axis. So that is not given clearly in that typing. So that's why here you have to understand that cylinder is along that y axis. The axis of the cylinder is coinciding along with that y axis, and here the platform is given a motion in x direction, x is equal to a cos omega t. So that's why here it is given x is equal to a cos omega t. Now you are supposed to find out there is no slipping between the cylinder during its motion, and you are supposed to find out what is the maximum torque acting on this cylinder. So now this the xy plane is here, this is cylinder, and the axis of this cylinder is coinciding with that y axis, and this horizontal platform, this platform is given a motion x is equal to a cos omega t. The platform is given a motion in x direction given by x is equal to a cos omega t, and thereafter you are supposed to find out what is the maximum torque acting on that cylinder. So here in this case, first of all, what is the acceleration of this? That is when you have given this motion x is equal to a cos omega t, and what is that acceleration produced there, and for that v is equal to, we are taking the dx by dt, and for that it is the minus a omega sin omega t is here, minus a omega sin omega t is there. And thereafter when you are coming to this acceleration, that acceleration is again, that is the dv by dt, and dv by dt is taken, and d by dt of minus a omega sin omega t, and further it becomes the minus a omega square cos omega t is that acceleration. Acceleration is the minus a omega square cos omega t is there, and thereafter you are given this is the minus a omega square cos omega t, and you are supposed to find out what is the maximum torque. Maximum torque means here also you have to get that maximum acceleration. So that maximum acceleration a maximum is equal to, so in that case it will be taken a omega square only, cos omega t can be taken as 1. Cos omega t can be taken as 1 if you want to get that maximum acceleration. So that's why a omega square, that minus sign is not required. That minus sign indicates only that is opposite to each other. So that's why that is not required. Here the magnitude only, it is the a omega square. So a maximum is equal to a omega square, and that a omega square will be acting on this cylinder like this. That a omega square will be acting on that cylinder, because here it is the pseudo acceleration that will be acting on that cylinder. When it is given such type of motion, when it is moving with some acceleration like this, then pseudo acceleration will be acting on, and that too it is the tangential. That too it is the tangential. So it is the a omega square is here. Now we have to find what is the torque acting on that, maximum torque acting on that cylinder. Maximum torque acting on that cylinder means tau maximum is equal to I alpha, and alpha I is there for the solid cylinder. So here you are given a cylinder of mass, so that's why for that cylinder it is taken as the mr square. Now it is nothing but solid cylinder is considered to be a circular disc in the top view. So that's why its formula can be taken as the mr square by 2, and alpha is equal to a maximum by r. So that is I is equal to mr square by 2, that is the natural axis of this solid cylinder, because the solid cylinder in the top view is nothing but a circular disc, and for the circular disc about the natural axis the formula is the mr square by 2. The same formula comes here also. So that's why it is the mr square by 2 is there, and a maximum by r. So that is 1 by 2 mr square. So that is the mr can be taken, and here it is the a maximum means a omega square. So the totally answer becomes 1 by 2 mr a omega square. That is the torque, maximum torque acting on that cylinder. So once again repeat this problem. So now here it is, this is the horizontal platform, and it is the solid cylinder is coinciding, that solid cylinder is coinciding with that y-axis. Its meaning is the axis of that cylinder is coinciding with the y-axis. Now this complete platform is given that motion, that is x is equal to a cos omega t, and the velocity is the dx by dt, it is a minus a omega sin omega t. Acceleration is equal to dv by dt, you are getting this one. If you want to find out the maximum acceleration, that becomes the a omega square, because this a cannot be taken as a 0, omega also cannot be taken as a 0, a cannot be taken, cannot be disturbed, and omega also cannot be disturbed, and cos omega t can be taken as the, omega t can be taken as the 0, so that's why cos omega t becomes 1. Now a omega square is there, and tau maximum is equal to I alpha, and I alpha, I is the mr square by 2, alpha is the a maximum, ultimately you are getting this answer. Now we are coming to this last problem. In that last problem it is mentioned, now so in this last problem you are given some figure. So that figure is nothing but that a square is here, and thereafter square is here, and it is the symmetrical laminas are there. So one is here like this. So next, here that axis is passing like this, and another axis is also there, that is taken as the AB. AB is that. And here this length is, that is the width is the 2a is taken, given here. Next after that you are given one more information, that is the 2a, that side is the a, and again a, and here also it will be a, like this. And in this problem you are given a symmetrical lamina of mass m consists of a square shape with a semicircular section over each of the edge of the square as shown. The side of the square is the 2a, and the mi of the lamina about an axis through its center of mass and perpendicular to the plane is 1.6 ma square. That you are given, it is the 1.6 ma square is given. That is the moment of inertia. The side of the square is the 2a, and the moment of inertia of the lamina about an axis through its center of mass and perpendicular to its plane. So that is perpendicular to its plane, passing through the center of mass means it will be like this. So that's why it is the passing through the center and perpendicular to the plane of the lamina is like this. And for that you are given that value, it is the 1.6 ma square. Now you are supposed to find out what is the moment of inertia of the lamina about the tangent AB in the plane of the lamina. So in the plane of the lamina. So that's why it is the 1.6 ma square is given. Here the specialty of this problem is, here you have to apply both the parallax theorem and the perpendicular theorem. Both the parallax theorem and the perpendicular theorem. Here first of all I explain this problem. Now this is the lamina is here, and that is not only that square lamina. So on that square lamina again it is a semicircular sections are there. So semicircular sections are here, and for all that about this natural axis the moment of inertia is the 1.6 ma square. 1.6 ma square, that is like this about this axis. In that case, so first of all you have to find out the moment of inertia about that xx dash. So about this xx dash we have to find out the moment of inertia, and for that we are applying the perpendicular theorem. So according to perpendicular axis theorem, so perpendicular axis theorem, and for that we are taking according to perpendicular theorem, it is the Iz is equal to Ix plus Iy. So here it is Ix plus Iy. Iz is nothing but already you are given. It is the 1.6 ma square is here. And Ix plus Iy is this one, and again we can take the same here also, because this is a symmetrical body. This is a symmetrical body, that's why Ixx dash, and again if you are taking this axis, both are will be perpendicular and both are equal to each other. So that's why it is the Ixx dash, and we can take another one also, that is the Ixx dash along this line, along this axis, that is the, so because of that therefore Ixx dash is equal to, that will be taken as the 0.8 ma square. That is the first equation. That is the first equation. Here what you are given, this is a square lamina, and onto the square lamina these are the semicircular sections are here, and that is the width is the 2a, and this one is the a is given, everything is given that information, and you are given one value, that is the moment of inertia of this complete lamina about O that is passing through the center and perpendicular to the plane of the lamina that you are given, it is the 1.6 ma square. Now here, if you want to find out the moment of inertia about this x dash, and for that we are applying that perpendicular theorem, and it is the Iz is equal to Ix plus Iy, and 1.6 ma square, that is equal to this one and again this one also. So that's why it is the Ixx dash plus Ixx dash, so that will be the 0.8 ma square. After getting this one, now you are supposed to find out, your target is to find out the moment of inertia about the tangent AB, and for that you are applying the parallax theorem, because the two axes are appearing, one is here and the another one is here, and both are parallel to each other, separated by a distance of the 2a. That's why according to parallax theorem, so according to parallax theorem, so in this case it is the, already we know that formula, so that is the IAB is equal to Ixx dash plus mr square, So this is the parallax theorem, and it is the Ix dash is equal to, already we know it is a 0.8 ma square is there, and plus m, and the distance of separation between them is the 2a, so that's why 2a whole square is there, and it becomes the 4a square. So it is a 4a square, and overall it becomes a 4.8 ma square is there, that is answer. So it is a 4.8 ma square. Now once again I tell you, so first of all, after finding this moment of inertia about this xx dash, if you want to find out the moment of inertia about this tangent, you have to apply the parallax theorem, because these two axes are parallel to each other, separated by distance 2a. So that's why IAB is equal to Ixx dash plus mr square. So it is a 0.8 ma square plus m, and r is the distance separation 2a whole square, then ultimately you are getting that 4.8 ma square. So thereafter, now so far we have discussed the problems based on this torque, parallel and perpendicular theorem, and again the moment of inertia. Now we are going to the second phase of that rigid body dynamics. The first phase consists of torque, parallax theorem, perpendicular theorem, moment of inertia, and the second phase is angular momentum and conservation of angular momentum, and maybe angular impulse also, and thereafter it is the energies. Next again the velocity, and again acceleration and time taken of a rolling body along that inclined plane. So all these are together in the, they are coming under that second phase. So now we are coming to the second phase of this rotatory motion. In that second phase, first we have to come from this angular momentum. Angular momentum or moment of momentum, that you call it is the L, that is indicated by L, angular momentum or the moment of momentum. So now first of all, in a translatory motion, that is the linear momentum P is equal to mass into velocity. Mass into velocity in translatory motion. And in a rotatory motion, that is taken as the L is equal to Rp. So if at all it is the angular momentum is the Rp. So not only in this that is angular momentum. So translatory quantities and again that angular quantities, rotatory quantities, they are connected by a bridge R. Suppose for example, S is equal to R theta is there. So now here it is the S is here, and again this theta is here, and R, S is equal to R theta. Linear displacement is equal to radius into angular displacement. Similarly, V is equal to R omega, and again the A is equal to R alpha. Next again the torque is equal to, that is a perpendicular distance, so that can be R, and again the force. Similarly here also, that is angular momentum. So that is the angular momentum that can be taken as the connected by Rp like this. So R is the bridge which connects the translatory quantities and again that angular quantities. Now L is equal to Rp. So S is equal to R theta, V is equal to R omega, A is equal to R alpha, and torque is equal to force into perpendicular distance, and here is equal to L is equal to perpendicular distance or that radius. Now it is the P. P is the linear momentum. R is the bridge which connects the angular quantities and again the translatory quantities. Now that is the L is equal to Rp, and it is the moment of a momentum, and here that is vectorially indicated by L bar is equal to R bar cross P bar. it doesn't obey commutative law. That's why you should not change the direction like this. It cannot be written as the P bar cross R bar. So it has to be written only that L bar is equal to R bar cross P bar only. And the direction of this L bar is perpendicular to the plane containing R bar and P bar like this. So that's why it is the P is here and again the R is here and L bar will be like this. So the direction of L bar is perpendicular to the plane containing both R bar and again the P bar. It is an axial vector. So L bar is equal to R bar cross P bar is here. That is the angular momentum, and thereafter that formula can also be taken as L is equal to I omega. L is equal to I omega. So now here L bar is equal to R bar cross P bar means implies L is equal to MVR. So unless otherwise mentioned, we always have to take a theta is the 90 degrees only. That angular momentum is the 90 degrees. And actually it comes RP sine theta. When the theta is taken as the 90 degrees, it becomes RP only. And thereafter it will be the MVR. Now L is equal to I omega and both are same. Because I is equal to mr square and again the omega is equal to V by R. And thereafter it becomes the MVR is here. So omega is equal to V by R and it is the MVR is here. So that's why both are same. Because of that reason, when you are solving the problems, depending on that information that you are given, depending on that you can choose this formula and again this formula or this formula. L is equal to MVR or the L is equal to I omega. Both of them can be taken.